Hey there, if you use a smartphone, a computer, or pretty much any modern tech, you're interacting with something built on a really revolutionary idea, object-oriented programming, or OOP. Today, we're going to pull back the curtain and figure out how this one concept totally changed the game for the digital world. So, let's start with the central problem that programmers were really wrestling with. As software got bigger and more complicated, the code just became this tangled mess. They desperately needed a way to translate our messy, complex, real world into clean, logical instructions a computer could understand. The answer to that puzzle, well, it was going to spark a revolution. To really appreciate just how big a deal this new way of thinking was, we first have to understand the world it replaced, a world that was built on simple but pretty rigid lists of instructions. Okay, so on the left, you see the old way, procedural programming. Think of it like a giant recipe. The code is just this long list of steps, and all the data, the ingredients, are just thrown together on one big counter. Any part of the recipe can just grab an ingredient and change it whenever it wants. Sounds simple, right? But as you can probably guess, it often led to total chaos. And believe me, those issues were a massive headache for developers. Because all the data was just out in the open, a function over here could accidentally mess up a value needed by a function way over there. This led to bugs that were an absolute nightmare to track down. It was kind of like trying to build a skyscraper with a recipe for a cake. The tool just wasn't right for the job anymore. So yeah, it was pretty clear that programmers needed more than just a small update. They needed a fundamentally new way to build software. It was time to stop thinking in long lists of instructions and start thinking in objects. And this quote right here, it gets right to the heart of it all. The entire foundation of this new approach rests on two incredibly powerful ideas, the class and the object. So let's break down what they actually are. So what exactly is OOP? Well, it's a huge shift from just writing instructions to actually creating these little self-contained objects. Instead of a long, drawn-out procedure on how to build and operate a car, we just design a car object itself. This virtual object knows its own data, like its color, its speed, and it has its own built-in abilities, like start engine or accelerate. It's a much more natural way to model reality in code. To really make this idea stick, let's look at the relationship between a class and an object using a super simple, real-world analogy. Okay, think of a class as the blueprint for a house. The blueprint itself isn't a house, right? You can't live in it. It's just the design. It defines what every house built from it will have: doors, windows, a roof. Now, the actual physical houses you build from that blueprint, those are the objects. You can build a whole neighborhood of them, each one a unique object, but all of them are reliably following that same master plan. Here's another way to look at it. We could create a fruit class. This class just defines that any fruit is going to have a name and a color. The strawberry and the orange here, they are the objects. They're both instances of the fruit class, but each one holds its own unique data. One is named strawberry and is red. The other is orange and is, well, orange. So to put it as simply as possible, the class is the blueprint. The object is the actual thing you build from that blueprint. Understanding this relationship is really the absolute key to unlocking the power of OOP. Okay, so now that we've got our building blocks, our classes, and objects, let's dive into the 4 core principles that give OOP its real power. You can honestly think of them as its superpowers. First up is encapsulation, and this capsule is the perfect visual for it. Just like it keeps its medicine safely contained, a class bundles its data and the functions that use that data into one single protected unit. They belong together, so they're kept together. The key idea here is all about protection. Encapsulation is like putting a protective shell around an object's data. Nothing outside that object can just reach in and interfere with it directly. This directly solves that whole spaghetti code problem we talked about, which prevents those accidental changes and makes the code way more reliable. Our second superpower is abstraction, which is all about hiding complexity. Think about driving a car. You only need the steering wheel, the pedals, and the gear stick. You don't need to see the thousands of complex parts working together under the hood. In programming, abstraction is the exact same idea. An object shows a simple public interface to the outside world while keeping all of its complex internal machinery private and hidden away. So abstraction is really about simplicity. It lets us use very, very complex things through a simple interface. And this is what makes it possible to build these massive software systems without getting totally lost in the details of every single little component. Next up, we have inheritance. And this one is super intuitive. Just like this cub inherits traits from the adult lion, a new class in our code, what we call a derived class, can be based on an existing base class. It just automatically gets all the properties and abilities of its parent. And the magic word here is reusability. Why reinvent the wheel, right? If you need a sports car class and you already have a general car class, you don't start from scratch. You just tell the sports car to inherit from car, and then you add the new stuff, like a turbocharger. It saves an incredible amount of time and effort. And this whole idea of inheritance can get pretty sophisticated. As you can see here, you can structure these parent-child relationships in a ton of different ways, from simple chains to really complex webs. We're not going to dive into every single type, but the key thing to know is that this flexibility lets programmers model very complex, real-world relationships right inside their code. And our final superpower is polymorphism. It's a fancy name, I know. It's Greek for many forms, but it's just this powerful idea that a single command can mean different things to different objects. For example, if you tell a circle object to draw itself, it draws a circle. But if you tell a square object that same draw command, it draws a square. Same command, totally different results. Pretty cool, right? Now, this ability for one name to have many forms can be handled in a couple of ways. Sometimes the program knows exactly what to do when the code is first written. Other times, it actually figures it out on the fly as the program is running. This second, more dynamic way is what gives programs this incredible flexibility to adapt to new and unexpected situations. So we've seen the building blocks and we've seen the superpowers. Now for the most important part. Why does any of this matter? Why did this way of thinking completely take over the world of software development? And here's the payoff. By building software out of these self-contained, reusable objects, we get programs that are more secure, way easier to update, and a whole lot simpler to understand. It's a system that tames complexity. These principles really provided the solid foundation needed to build the massive, intricate software that powers our modern world. For decades, object-oriented programming has been the bedrock of software development. From the operating system on your computer to the apps on your phone, the principles we've talked about today are literally everywhere. But you know how it is. Technology never, ever stands still, which leaves us with a final big question. What new idea, what new paradigm will shape the next generation of software?